Good evening. I am Madhava Venkat of ECA section. My topic is Fast Fourier Transform. A fast Fourier transform is a mathematical model which helps to transform the signals between two different domains, such as transforming signal from frequency domain to time domain and vice versa. First of all, for this simulation of fast Fourier transform, I have taken a simulate signal in the functions tab. When we go to functions, express, input, we can find the simulate signal module. I have taken two simulate signal module, and this function of the simulate signal module is to allow us to create a waveform according to a number of different parameters like frequency and amplitude. So I have taken two knobs. The F1 knob is connected to the frequency of this first simulate signal, and F2 knob is connected to the frequency of the second simulate signal. So these two simulate signals are connected to a AND operator or a plus operator, which I got from the numerical part of the functions tab. This helps in adding the sine wave that we get from the first simulate signal and the second simulate signal. I have also attached two waveform graph to each of the simulate signals. F1 waveform graph is attached to the sine of the first one, and F2 is attached to the sine of the second one, and the result of the added sine waveform is shown in this add graph. And later I have connected this result to the spectral measurement. I got the spectral measurement from functions, express, signal analysis, and here I got the spectral measurement. The main function of spectral measurement is to examine the noise floor of a signal or the power in a specific frequency range. And once we attach the spectral measurement, a pop-up window arises. In that pop-up window, we have to mention the necessary parameters, and later in this pop-up window I have selected power spectral density, which is shortly mentioned as PSD. We can also opt with magnitude RMS also, and I have selected a linear result. We can even get results in decibels, but I have selected linear result, and in the selected measurement tab I have selected power spectral density. And under this window we are having several things like Hanning, Hamming, Blackman, Harris, exact Blackman, like these. So these functions are nothing but these Hanning, Hamming are all functions which alters our signal, tapering it to nearly zero at the beginning and the end. So this is the function of this window. So there are different types of windows like Hanning, Hamming, and once selecting these parameters, I'm clicking OK. And later by clicking on this PSD, by doing a right click, we can create a graph indicator, and once I select this graph indicator, I get this FFT graph indicator. So that graph indicator is shown here in this front panel. The fourth graph is the FFT. FFT means fast Fourier transform. And later, for getting a timer, I am going to the functions tab. In functions I am going to timing. In timing I am selecting wait. So this wait milliseconds helps this particular output to wait for 100 milliseconds. Once I get this, I can right click on this. I will go to create, and I will create a constant, and once I create a constant I get this small box, and here I have typed in 100, which means that it will wait for 100 milliseconds. And after doing all these things, I'm enclosing my entire function with the help of a while loop, and then I am creating the stop function also. So once I run this program, this is the output that I obtain here. And these two knobs that we are seeing in this front panel helps in increasing and decreasing the frequency. So this f1 is the frequency that I get from the first. The f1 frequency helps can be adjusted with the help of the f1 knob, and the f2 frequency can be adjusted with the help of the f2 knob, and all the outputs that we get in all these are all completely sinusoidal outputs, because the output of a fast Fourier transform is completely sinusoidal. So all are sine waves that I have obtained here. And even I can change the PSD to magnitude, and I can check my outputs. So output can be received in any manner. And some real-time applications of fast Fourier transform are speech recognition, music classification, noise reduction, etc. It is also used in digital signal processing, and in especially in the field of audio, it is used in changing or reducing the noise of various acoustic sounds. And in this spectral measurement component that I have added here is plays a main role in this fast Fourier transform. Here this PSD that is mentioned here can be changed to magnitude also. With this, my output is displayed here. These four outputs, the final output is the FFT output, which shows the final fast Fourier transforms output. F1 output is the output or the frequency of the first simulate signal. F2 output is nothing but it is the frequency of the second simulate signal. This knob F1 corresponds to this F1 graph. This knob F2 corresponds to the F2 graph. You can see the change as I increase and decrease the knob of F2. And this add graph shows the variation of the final result. Once it receives the signal from F1 and F2, the final result is shown by the add graph, and the FFT graph shows the fast Fourier transform output. The fast Fourier transform output is calculated with the help of mathematical expressions, which are especially designed for fast Fourier transformation. Thank you.